Any questions about anything before we get started? Hopefully Friday I won't be so blasted warm. All right, so last time we talked about logarithmic functions, talked about domain, range, asymptote, those kinds of things. And then we did a couple of problems at the end of class where we were finding domains of certain log functions that had different inputs, if you will, than just an x, right? We had basically a composition of functions. So I just wrote one more problem up here with looking to find a domain of a particular log function that also reviews some of the stuff that we talked about in the previous chapter, which was about solving inequalities. So when we're interested in domain of any logarithmic function, what are we interested to know about the inside of the function? What has to be true about the inside of the function in order for it to be in the domain? What are you not allowed to take a log of? You can do log of 0, what else? Negatives, right? Anything that you do the log of, it has to be a positive number. Remember that the domain of logarithmic functions is the same thing as the range of exponentials, right? Because they're inverses of each other. So the domain of any log function is always 0 to infinity. So I need to make sure that what's on the inside here is greater than 0. So we need to make sure that our inside here is greater than 0. And now this should look like a problem that we talked about before, right? This looks like those rational inequalities that we were solving back in section 3.7. If I'm going to solve a rational inequality, what do we want to do next? Say it again. So what would you do at the bottom then? Okay, good. You know, I want to factor the bottom. I could also factor something out of the top, right? There's a common factor of a 3 in there. Okay. How does the bottom factor? Good. X minus 8, x plus 3. Remember also when you're doing these rational inequalities or the polynomial inequalities, you need to make sure we have 0 on one side. Which this already has 0 on one side, right? What do we do next? Why did we factor everything? So we're going to find the zeros, right? We want to find the zeros of the top and the zeros of the bottom. What makes the top 0? What do you plug in for x to make the top 0? 2? Yeah, it's not a trick question, right? What about the bottom? And? Good. Right? The next step when you're doing these rational inequalities is making sure that we have figuring out where the top is 0 and where the bottom is 0. What do we do next? Yeah, good. Make a sign chart. Good. So we've got -3, we've got 2, and we've got 8. Pick some test points. Picking something that's less than -3. -4. We put -4 in for x. The top, is that going to be positive or negative? Positive. Good. This term will be negative, and that term will also be negative. So if we have positive over negative times negative, what's it make? All things positive. Good. Pick something in between -3 and 2. 0. Now, always pick 0 if you can, because it's one of the easier ones to plug in, right? Put 0 in for x. The top is positive. This factor is negative. That factor is positive. So you get positive over negative times positive makes negative. Good. Something between 2 and 8. 3. The top is negative. That's also negative, and that is positive. And so the whole thing will be positive, right? Because we got 2 negatives there. And then finally, pick something bigger than 8. 9. The top will be negative, and then each of those will be positive. So the whole thing will be negative. Good. And what are we looking for, the positives or the negatives? The positives, right? Because again, the input for the log has to be positive. We can't put negatives into a log, right? So we're looking for the positives. So what's our domain going to be in this case? Okay. Is it a parenthesis or a bracket? Good. Because? Yeah, it's not equal to, right? Doesn't matter if it's in the top or bottom in this case, right? It's not equal to, so it'll be a parenthesis. And then so the other one will be 2 to 8, and those will both be parentheses as well. So again, for the real other reasons why I wanted to go through another example of this, besides the fact that we did it right at the end of class last time, was so that I could also review doing the stuff with the rational inequalities. Questions on that one? All right, so let's go on and do some examples here of evaluating some logs before we go into a couple of new definitions of some specific log functions and then get into some properties today. So remember that logarithms are exponents, right? It's the exponent on the base that you need to get the input. So if you're able to write the input as a power of 4, you should be able to easily answer this question. Can you rewrite 1/16 as a power of 4? 4 to the negative, which what I just heard. Yeah, 4 to the negative 2, right? The negative because it's flipped upside down, and the 2 because 16 is 4 squared, right? So again, logarithms are exponents. What this is literally asking you is, what exponent do you need on 4 to get 4 to the negative second power? Not a trick question. What exponent do you need to put on 4 to get 4 to the negative 2? So what exponent do we need on 4 to get 4 to the exponent negative 2? Negative 2, yeah, it is the exponent. Remember, logarithms are exponents, so it's literally picking off the exponent for you. Okay? So if you're able to write the input as a power of the base, then all it's asking you to do is figure out what that power is. Okay? So let's look at the second one. Can you rewrite the input, which is 1 over 9 to the, or excuse me, 1 over the 7th root of 9? Can you write that as a power of 3? Maybe do that in a couple of steps. How do you rewrite the 7th root as a power? Good, yeah, it's a fractional exponent, right? Remember, roots are fractional. You can rewrite them as exponents as a fraction. The denominator of your fraction tells you what root to take, right? All right, so again, can I rewrite this as a power of 3? Well, ignore the 1/7 for the time being. Can I rewrite 9 as a power of 3? What is it? 9 is 3 squared, right? Oops, not 9 squared, 3 squared. So I just replaced the 9 with the 3 squared. And this is just a little bit about remembering what we do with exponents in this situation. What do you do with the 2 and the 1/7 when you get exponents in this situation? What do you do with your exponents? Multiply them. So we'll just get 2/7. Good. And then just like in the previous problem, I'm doing probably more steps than I really need to do. We can bring that up to the top and make it a negative exponent. Right? And now again, what power do you need on 3 to get 3 to the negative 2/7 power? Negative 2/7, right? It is the exponent. Remember again, logarithms are exponents, right? It's trying to pick off the exponent that's on the base. So I would get negative 2/7 there. Is okay so far? We're going to do more practice with these on the next page too, but is okay so far? Okay. Now, sometimes it's a little hard to see how to write the input as a power of the base. Sometimes it's a little difficult, okay? In particular, 125 is a little bit harder to see what power you might need to get on 125th. So there's another way that we can go about doing these, and that's to rewrite this in the equivalent exponential form, and then try to see if we can work with the exponential form to help us see what's going on, okay? So remember, if this is equal to, say, x, I don't know what the x is to start with. How do we change this from a logarithmic expression, a logarithmic equation, into an exponential form? How do we rewrite this as an exponential form? We did this last time. One over 25 to the what power? So remember, this is the base of the log, so it's also the base of the exponential. What do we use for the exponent? I did this last time. Should be in the notes from last time. We had numbers rather than letters, but it should be in there from last time. We had going from exponential to logs and logs to exponentials. Maybe on the second page. Yep, so we have a logarithmic equation like we have here on the second page, right? I want to rewrite it as an exponential equation instead. Remember, what are the outputs of logarithmic equations? What are the outputs of logarithms? Logarithms are exponents. So where does that exponent go on the base? Where does the x go for the base? Where does it go? It's the exponent. Yeah, that's the output. Remember, logarithms are exponents. That's the exponent on the base. So that x goes on the base. And that has to equal the 4th root of 125. That's the equivalent exponential form, right? Remember, logarithms and exponential functions are inverses of each other. Inputs become outputs, outputs become inputs, right? The output of the logarithm is the input for the exponential. The input for the logarithm is the output for the exponential. Okay? All right. As I drop things on the floor. Sorry. All right. Can we rewrite this both sides? Can we rewrite both sides as the same base now? Rather than trying to rewrite 125 as a power of 125th, can I rewrite both sides of this equation using the same base? Can I use the same base on both sides to write each number? For example, what can you write 25 as something to a power. What can you write 25 as? 5 squared, right? So here I would have 5 to the negative 2 raised to the x power. Can you rewrite 125 also as a power of 5? What is it? 5 to the... So the 1/4 is the power for the rational, right? What about the 125 piece? 5 to the third? Yeah, I heard you say. Yeah, 5 to the third, right? So if 125 is 5 to the third and you're doing the fourth root, it'd be 5 to what power? Good, 3/4, good. The 3 comes from the fact that 125 is 5 cubed. The fourths comes from the fact that you're taking the fourth root. Okay. Just like last time, what can I do with these two? Multiply. Good. So we now have 5 to the negative 2x equals 5 to the 3/4. Okay, now we're almost done. These are outputs of an exponential function, right? We've got 5 to a power on the left-hand side, 5 to a power on the right-hand side. Remember that exponential functions are 1 to 1. Plug in different things for the inputs, you get different things for the outputs. That's what 1 to 1 means. Or set it in reverse, if you got the same output twice, you must have plugged in the same input twice. Right? So since the outputs are equal, we must have that the inputs are equal. Oops. The input on the left-hand side is negative 2x. The input on the right-hand side is 3/4. So we must have negative 2x equals 3/4. Can you solve for x now? Yeah. What do you get? Negative 3/8. Good. And so that is the answer to the original problem. Remember, we just said we're going to let x be that value. That is the log that we wanted. I feel like we should do another one of those. I can make one up. Let's say I want to do log base 243 of the 10th root of 1 over 27. Again, unlike the first two we did, I don't think it's very easy to recognize the power that you need on the 10th root of 127, excuse me, the power you need on 243 to get the 10th root of 127. So let's do the same technique that we did last time. Let's first set this equal to some variable. There's nothing special about x. You can make it whatever letter you want, or if you want to draw an emoji for your variable, I don't care. First step, rewrite this in the equivalent exponential form. Change this logarithmic equation into an exponential one. What's the base of the exponential function we're going to use? 243. What's the exponent? X. And the output will be, good, the 10th root of 1 over 27, right? Remember, all this is doing is just using the fact that we've got inverse functions, right? Inputs become outputs, outputs become inputs. Now, much like what we did in the previous problem, notice in the previous problem, I recognized that both sides of the equation could be written as a power of 5. Okay? Do you see a number that I can write both sides of this equation in with the same base and a power? What number do you might want to use for the base for both sides here? Probably use 3, right? In particular, 27 is 3 to what power? The third, right? 243 is 3 to what power? You get a calculator checking. Just start plugging in powers. Or the fifth, yeah, good. So the left-hand side will be 3 to the 5th to the x. Or if you want to go ahead and write it as 3 to the 5x right away, that's okay, because we're going to multiply the exponents again. What about the right-hand side? What power are we going to have there for 3? It'll be 3 to the negative, I heard the other one, 3 over 10, right? Why is it negative? Good, because it's flipped. Fantastic. It's flipped upside down, right? It's 1 over 27. The 3 comes from the 3 cubed, and the 10 comes from the root. Good, fantastic. Are they okay with that? Okay. All right, so again, we multiply here, right? Right? So we would have 3 to the 5x equals 3 to the negative 3/10. We now have the same base on both sides, right? So we have essentially the same output for the exponential function. Well, the outputs are saying what has to be true? Inputs have to be the same. Good. Because again, exponential functions are 1 to 1. So at this point, we get 5x equals negative 3/10. And then to solve for x, we just need to divide by 5. And like I said, I think it would have been difficult to recognize off the top that the 10th root of 127 is 243 to the negative 3/50th power. That seems hard to do at the start, right? So that's why it's a little bit easier here to rewrite it in exponential form and get the same base on both sides. And then figure out what the x has to be. Questions on that one? Is that all right? I'm getting lots of feedback today. We okay with that? Okay. All right. So basically same stuff on the next page. There's just a couple of different definitions that we have here. And if you notice, pardon me, if you've noticed, we can certainly do the log base anything we want as long as the base is positive and not equal to 1. Just like when we had exponential functions, right? The base needed to be positive and not equal to 1. But on your calculators, you may notice that there's only 2 buttons. And you actually, to start off with, you may only recognize that there's 1 button that's a logarithm. So how can we, one of the things we'll talk about in the next section is how can we convert log base anything to any other log base that we would like. 2 of them that are very, very common that we'll want to use are what are referred to as the common log, the common logarithm, and the natural logarithm. The common logarithm, the reason why we call it common is because it's also the same base as what we count with, right? You have 1 space, 10 space, 100 space, 1,000 space. That's base 10, right? So common log is log base 10. So it means the base of the underlying exponential function that you're using is 10. You might understand why we use a common log. If you've done anything in science and written things in scientific notation, it's 10 to a power, right? As an exponential form for that with a base of 10. So you might need to do a common log with a 10 to go along with that. When we do common log, we don't put a base. So if you see log and no base, it's understood that it's base 10. Okay? If you see log with no number written below it as a base, you assume it's base 10. That's what common log is. Okay? The other one that comes up a lot is the natural logarithmic function. Remember, we also had the natural exponential function. What was the base for the natural exponential function? What letter did we use to denote the base of the natural exponential function? That was that special number. It was a little bit less than 3. E, right? So the natural logarithmic function is log base e. The notation for the natural logarithm function is ln of x. That's an L, not an I. Some people will emphasize the fact that it's an L by using a cursive L rather than a lowercase l, because it does look like an I. It's an L. So the natural logarithm is ln of x. The reason why it's ln and not nl is because it's an abbreviation for the Latin. Latin is logarithmus naturalis. That's why it's ln. I'm sure you care a lot about why it's ln and not nl, but that's what you get from me, useless information. All right. The important thing is that this is not an I, it's an L. Okay? You'll see these two buttons on your calculator. You'll see an LOG and you'll see an LN on your calculator. Little buttons that move on there. Assuming you have a scientific calculator, little buttons that move on there. All right. So let's do some of these. And we'll evaluate these the same way we evaluated those first couple. I want to see if I can for the first two, let's see if we can rewrite the input as a power of 10. The first two are common log, right? LOG of 10,000, LOG of whatever I wrote, fifth root of 100, right? Can you rewrite 10,000 as a power of 10? I am so glad that they find me with the leaf blower all the time. 10 to what power? I'm sorry? The fourth, right? Remember that it's not too hard to figure out the power on tens if you just figure out how many decimal places you have to move, right? To get a 1, I need to move that 4 places to the left, so it's 10 to the fourth. And again, now we're just asking the question, what power do you need on 10 to get 10 to the fourth power? 4. Yeah. We're just picking off the exponent. Next one, let's start with, we'll do the fifth root in a second. If you can do it at the same time, that's fine. So let's just do the 100th. How can you rewrite 100th as a power of 10? 1 over 100, good. Be 1 over 100, and so that'll be 1 over 10 to the second. Yep, good. Yep, so 100th is 1 over 100, and 100 is 10 squared. Now can we rewrite the input as a power? This is a power of 10. How would I rewrite that as a power of 10? Good. 10 to the negative 2/5. Again, running through each piece, the negative is because the decimal is also flipped, right? And we write it as a fraction. The decimal tells us that we want to move the decimal point 2 places to the right, so we'll use a negative, or it's flipped upside down. The 2 is for the squared, and the over 5 is for the fifth, right? Those 3 pieces. So then the answer to this is what? Negative 2/5. Good. And if you were to type this in your calculator to start with, if you would have typed in LOG of the fifth root of 100th, your calculator would spit out 0.4, which is 2/5. Okay. All right, same idea here. Remember again, when you see ln is an understood base of e. So this question is asking, this first one is asking you, what power on e do you need to get e to the 6th power? 6. Yeah. Again, another way to think about it is that logs and exponentials are inverses of each other. You did the exponential function and then you did the inverse. You plugged in 6 into the exponential, took that, plugged it into the log. They undo each other, so you just end up back where you started. was a 6. Another way to think about it. What do you think we should do in part D first? Notice, what did we do in part B first? We rewrote the input as a power of 10 because it was log base 10, right? Natural log is log base e, so I should write the input as a power of e. Good. How do we rewrite the input as a power of e? E to the negative. So negative 3, and then the fourth root will give me a 3/4, right? The negative because it's flipped. 3 because we have e cubed. Over 4 because it's fourth root. Right? There's 3 pieces there. You see it? And now we can read the answer off. What's the answer here? Negative 3 volts. What questions do you have on those? All right. So, why do we care about logarithms? Besides the fact that they're inverses of exponentials. Well, we've got problems that involve we've got problems that will involve logarithmic equations. Logarithms have applications to different types of scales. If you're familiar with the Richter scale for earthquakes, that's what we refer to as a logarithmic scale. If you know about decibels for sound level, that's also a logarithmic scale. So logarithms have different applications. If you need to solve equations with exponential functions, logarithms pop up. Exponential functions pop up not only in science but also in business. So one of the many reasons why we talk about logarithms. All right. So we had some laws of exponents that we talked about. We also have some laws of logs that go along with them. So remember that logarithms, again, are exponents, right? What do you do with exponents when you multiply two things together? What do you do with the exponents? Add them, right? So our first law of logs is exactly that same idea. When you have the log of a product, that means that you add the two logs together, not multiply, it's add. Okay? Again, the idea behind this one is what you should think about is that when you multiply, you add exponents. That's where this property comes from. Okay? What about the second property here? Well, instead of multiplying, we are dividing. What do you do with exponents when you divide? Subtract. So how do you think we can rewrite this? Log base a of x minus log base a of y, right? And again, the right way to think about this is to think when you divide, you subtract exponents. Okay? Now, this last property might be a little bit trickier to think about, but pardon me, it goes back to those ideas that we were in some of those problems we did before when I said, when you've got something raised to a power and then you have another power on the outside, what did you do with the powers then? Multiply the exponents, right? So this is the same kind of concept here. We can bring that power down in front and write it as r times log base a of x. So this is when you have something raised to a power and you raise it to another power, you multiply the exponents together. These are the correct laws of logarithms. What I have down at the bottom of that page are some very, very, very common mistakes that students make trying to invent new logs properties that don't exist. Okay. The first one, what would you really like for that to be? What would you like to be able to do with that log relative to the sum? So, for example, if you had 3 times x plus y, what would you do with the 3? Distribute it, right? You really, really want to do that, right? You really want to be able to break that log up over the sum. Remember, though, it's not multiplication. It's a function, right? The x plus y is on the inside of the function. This is not multiplying, okay? So this is not the same thing as log base a of x plus log base a of y. Okay? It's not the same thing. Logs do not break up over sums, just like square roots do not break up over sums. Just like exponents don't break up over sums. You cannot break this up. So similarly, the second one here is not break up over subtraction. Okay. We already have expressions for these two things. This would be log base a of x times y. This would be log base a of x over y. Okay. They do not break up. Now the last one looks a little bit weird. Compare it to what I have at the top of the screen. At the top of the screen, what does the exponent of r apply to? Just the x, right? At the bottom of the screen, the r applies to the whole thing. Those are different, right? So in this case, you're not allowed to bring that r down in front. Okay. This is not the same thing, okay, as this. Pay attention. These are not equal to, right? These are not true statements. Okay? These are very, very easy little mistakes to make as you go through them because it's very, very tempting. Just to make sure you keep them straight of what is a log property and what isn't. All right. So these next few problems that we have are just different types of things that we'll do when we're solving problems later on. In particular, when we're solving equations. Sometimes we will want to put things back together and write it as a single log. Sometimes we'll have something written as a single log and we'll want to break it into multiple pieces. Okay. All right, so let's look at the first one here. It says, take something that's already broken up and rewrite it as a single thing. Okay. So let's look first at what we have as these individual pieces. Notice that each of those individual pieces has a number, a constant, out in front, right? Okay. Going back up to our log properties that we wrote on the previous page, looking at that last one, if I have a number out in front, what can I do with that number? Yeah, put it on the power for the inside, right? So if I look at that first one, what can you do with that 5? How can we rewrite that first term? It'd be log base b of what? X to the 5th. Good. I can take that constant and move it back up to the top. How about the second term? Yeah, log base b of z to the 3rd. Good. And then minus, what can you do with the 2? Move it to the top again. Yep, move it as an exponent. So I have log base b of y squared. Still haven't got it as a single logarithm, but that would be the first step that I would do, right? Take those constants, move them up, right? So far, so good? Okay. Let's do this a step at a time. If you're able to do the whole thing at once, fantastic. But let's do it a step at a time to make sure that we have everything and we're making sense of everything here. Let's just look at the first since we would add and subtract in order from left to right, let's just look at the first two. I've got a plus sign in the middle. Again, going back up to our properties of logs, if you have a plus sign in the middle, how would I rewrite something with a plus sign in the middle? What do I write as a single log on the inside? What do you do with the insides? Multiply, right? So if I go back down, how can we rewrite just these two? Just the first two, how would you combine them? Next to the fifth, is it plus or is it multiply? Good. Yeah, it'd be times z to the third, right? We would multiply the insides together. Good. So again, we're just trying to put them back together, right? Okay. Now I've got the difference of, it's still not to a single logarithm yet, right? So I have two logs left, but I've got a minus sign in the middle. Well, when we had a plus sign in the middle, we multiplied, right? When we have a minus sign in the middle, what do we do? Divide. So how are we going to write this then as a single log? Good. Exactly right. And so then this would be your final answer for that one. Again, if you were able to go from this step to that one, that's perfect. You've practiced enough. You can do that. That's great. But again, if you need to, do it step by step, right? Do the first two, combine them, combine it with the next one, and keep going for how many of them you have. Questions on that one? Okay, let's look at part B. I've got a 1/3 outside the parentheses, and then I've got some stuff going on inside the parentheses. What do you think we should probably work first? Inside the parentheses. Let's do that first. Good. Looking inside the parentheses, just at those two pieces, what do you think you want to handle first? The 3, right? Want to handle that 3 that's up in front? So how can you rewrite that second term? Y to the 3rd. Good. What can you do next? Yep, change it to multiply. Log base b of x times y to the 3rd. Okay. And then lastly, what can we do with the 1/3 that's out in front? Make it an exponent, good. And that exponent is going to apply to the whole inside. So you'd have log base b of xy cubed to the 1/3. And that's honestly good enough for our purposes, but if you really wanted to, since you've got a product on the inside, what can you do to this 1/3 with this 1/3? Because it's multiplied on the inside. I could distribute it to each piece, right, if you really wanted to. So you could rewrite that inside as, you don't have to, but you could certainly rewrite that inside as x to the 1/3 times y. Because you can distribute that exponent to each one. Instead of multiplying, or plus sign, but you couldn't do that. Work on that next part for a minute. We'll chat about it, and then we'll be done for the day. talking about it? What did you handle first? Yeah, the coefficients in each of them. Good. So you rewrite the first one as good, and the second one good, and the last one good. So what everybody got for first step, moving those up? Okay. What did you do next? Combine? Did you do it all at once, or did you do it step by step? Okay, step by step. So you did the first two together. What did you get when you combine the first two together? Good. Right, in that case, we multiply, right? And then final step, divide. Good. So you'd have x cubed y to the fourth over z to the 1/2. And you can put parentheses around it or not. We understood that it was all inside anyway. It was okay? Happy with that? Okay. All right, so next time we'll play more with these properties. Notice again here we were practicing putting them together. The next example, let's practice tearing them apart. And then we'll do some more properties of logs next time. So we'll see you on Friday. Like I said, hopefully it'll be cooler on Friday than it was today. Have a good one, everybody.